This is a Schwarzschild black hole, rendered in Python and OpenGL, using a technique called four-dimensional ray tracing, which makes use of some actual equations from relativity. We can change the skybox, add an accretion disk, change the camera angle, or the distance away from the main dark region, called the black hole shadow, to kind of fake this sucking in effect. We can also make the camera follow a true inwards gravitational trajectory, sucking us in so fast our field of view is distorted due to special relativity, just like in this other demo of what's called flat spacetime that we'll also look at. I also tinkered with this more accurate model, which supports rotating black holes like this, where we can see the characteristic ring of photons encircling the main shadow, which compresses to one side if we increase the spin. But it's still clearly a work in progress, though it does look kinda cool when you fall in. I also used the exact same rendering technique to simulate special relativistic effects alone, like this television screen traveling near light speed, playing a looping video, which gets all jumbled up as we enter its reference frame. The coolest part about all these demos from an implementation standpoint though, is they're actually not so different from one another. They're actually using the exact same algorithm under the hood, just on different space-time metrics. Meaning, all these sorts of weird visual effects and distortions we see here, the field of view expansion, the lines on the floor becoming parabolic, the squashing and stretching of objects, even perhaps my favorite black hole effect, this Einstein ring, which warps the skybox behind it and gives the accretion disk its characteristic look instead of this boring hula hoop, you automatically get all of these effects to pop out essentially for free if you understand the basic concept of how we model four-dimensional curved spacetime, whatever that means, and simulate a camera's trajectory and light rays inside it, whatever all that means. The hope here is not just to describe the final algorithm to you, which actually isn't super difficult to code up in and of itself, but to rather explore the core essence behind how we even begin to think about this abstract object called curved spacetime, though we will do it while staying grounded in its concrete application to making these sorts of exciting visuals. But I should also mention that the core principles of spacetime and relativity we'll get into here have many other applications in real scientific research too. Alright. So the basic idea here to draw each frame of our black hole simulation is calculating the paths taken by light rays emitted from a fictitious camera located somewhere in our scene, representing the observer. And as the explanation typically goes, when these light rays reach this sort of region of distortion called the Einstein ring, the rays bend around it, much like how light bends when it passes through a piece of glass. But this is completely fake news, and a misrepresentation of the much cooler reality of what's actually going on here. While yes, the end result here is visually akin to a kind of lensing effect, hence the name gravitational lensing, a very real phenomenon observed in actual astronomical data. In reality though, as the saying goes, the light rays aren't being bent at all. Instead, it's space-time itself. Now we hear this all the time, right? This bending of space and time, which you can kind of visualize using these cool grids like this, or using the more popular bowling ball on bedsheet videos that kind of explain gravity using gravity. The problem when trying to visualize something like space-time, which is mathematically described as a smooth surface, is it feels like you'd always need some further notion of outside, wherever this thing is floating around in, which is kind of problematic if the thing you're trying to describe is literally supposed to be the whole universe. But there's actually an even deeper reason why this sort of visualization here falls apart. In relativity, space-time isn't even the same kind of surface as a sphere or torus or this kind of blanket-looking thing, which are all Riemannian manifolds, meaning they all look identical to flat space if you zoom in close enough to any point, where the geometry is nice and approximately Euclidean like we're more used to, even though it might be crazier on a global level with greater than 180-degree triangles and so on. Space-time, on the other hand, as it's modeled in relativity, doesn't even have this basic property that gives all these example surfaces their characteristic smooth, surfacey look. Instead, as it turns out, even at a zoomed-in local level, it has what's known as Minkowski geometry, which is weird and non-Euclidean. So our entire understanding of what the word surface means kind of goes out the window. Oh yeah, and on top of all of this, it's also four-dimensional. Got it? If not, here's the actual mathematical definition of spacetime, which hopefully clears things up. Okay, but really, how do we even make sense of any of this? The main trick here is to use a tool from a subject in math called differential geometry. The idea is that instead of trying to literally envision spacetime as a whole surface kind of floating around somewhere and modeling it that way, we keep it abstract and instead imagine tearing and flattening out little patches of it on diagrams like this, called coordinate charts, much like how we chart out the surface of the Earth. For instance, this is a coordinate chart for Schwarzschild geometry, the curved spacetime geometry outside a non-spinning black hole, like this one. The point here is it's kind of just a made-up picture, designed for humans to make sense of this particular patch of spacetime, and we'll do all our ray tracing calculations inside charts like these. There are many such coordinate charts you can use to describe the same patch of spacetime, like the Kruskal or Eddington-Finkelstein one. Just like how you can have many different maps of the same region on Earth. The only challenge here is we don't have the mental crutch anymore of getting to imagine the full surface as floating around somewhere. The charts are all we have. Now, what took me some time to wrap my head around when I first dealt with spacetime charts like this one is that the axes will often be labeled in any which way. Like here, they're labeled R and T. And what's kind of trippy here is neither of them actually represent space nor time, at least not in the usual sense for any particular observer. They're just measly coordinates that might as well be named alpha or dinosaur. And to make matters worse, curves like these ones, representing light rays entering and leaving the black hole's so-called point of no return at this coordinate r equals 2m, are actually straight lines that simply appear curved due to our choice of chart. It's just like looking at flight paths on maps of the Earth, which often look curved, but they're actually straight in the sense of the Earth's geometry. Meanwhile, a line of latitude like this one, which appears straight inside this map of the Earth, is actually considered curved in spherical geometry, because if you imagine driving a large vehicle along it, you'd constantly have to keep turning the wheel, which isn't the case for a curve like this one. Pretty cool, isn't it? Anyways, the upshot is you can't visually trust what you see in a coordinate chart, because lengths, angles, directions, shapes, everything can appear distorted and weird, and it all depends on what chart you're using to describe your patch of spacetime. Another challenge here is that spacetime is 4-dimensional, so all its charts are also 4D, unlike the Earth's, meaning we should really have two more axes here, typically labeled theta and phi. And even though we'll need these full set of 4 coordinates for making the visualizations, we'll omit these two from the diagram to keep it simple. Alright, now here's how our algorithm will roughly work. We choose a chart like this for the patch of spacetime we're interested in visualizing, and then we start by representing our camera at each frame as a point sweeping along an observer trajectory like this, called a world line. Ooh. Now, in a normal graphic setup, like in a 3D art software like Blender, you can animate a fictitious camera like this to follow a certain path in a scene, like this room I modeled. And when you hit that render button, it hands you back a list of images taken from the point of view of that camera as it sweeps around the path. And the algorithm it uses to compute each image is called Raytracing, which is actually a pretty neat trick if you really think about it. What's going on here is, we're imagining that my real-life laptop screen in the real world is a window into the simulated realm. And that's literally what this little camera's rectangle represents here. And if we match the correct focal length here, the distance from my real physical eye to my laptop screen, the Raytracing algorithm computes the line segment from your real eyes to the ith physical pixel on the screen and continues it into the simulated 3D world, where it bounces around to see where that light must have come from before ending up at your eyes, giving you the illusion that your laptop screen is a window. It's a kind of reverse process, because we're simulating light rays backwards and seeing where they would have come from to reach each pixel. So how the heck do you work that into this whole space-time craziness? Well, there's already one major issue in this whole ray tracing setup for us. At each animation frame, we're essentially assuming each object in the scene is frozen in time, as though the universe is patiently waiting for us to shoot out our rays of light, and for those rays to take their sweet time to reach the objects in the scene and then bounce around to accumulate the final pixel colors. And for most cases, this is a perfectly reasonable assumption because of how fast the speed of light is. But what about when we have objects in the scene that are themselves traveling near light speed? Clearly in the real world, such objects would move by the time a light ray bounces off them and reaches the camera. So if we simply ray trace by freezing the objects as they are at a given frame, we'll get the wrong image. So we somehow have to track our rays backwards through time like this to properly calculate where they came from. In other words, we have to model in an extra time dimension, perhaps like this, where each slice represents one animation frame. Now to compute the image at, say, this last frame, we'll actually need to connect together the cubes from all the different times like this to form a 4-dimensional object. And now, we'll need to trace our rays not just inside a single frozen slice of space like we were doing before, but at an angle through multiple such slices and testing whether it ever pierces this four-dimensional version of the cube. Problem solved, right? Well, it's a good start, but now we're seasoned physicists and we understand that spacetime is not quite as simple as an IHOP order of stacked 3D spatial pancakes and doesn't have this simple Euclidean geometry that we can chart out like this. The real solution, going back to our chart of Schwarzschild geometry, looks more like this. At every point along the camera's world line here, we have to compute the actual spatial pancake, which can look all distorted and wonky in our chart. But it still instantaneously represents the observer's experience of space at the moment. And as the observer moves through our little spacetime blob, so does this surface. And so, any given observer's experience of this region of spacetime can be entirely different depending on how their moving trajectory drives around what's known as this space-like surface, or now slice, containing everything that the observer considers as part of their now, just like the horizontal slices we had in our little thought experiment before. Pretty neat, right? And so, if we want to properly handle that time delay problem of light, we have to shoot out rays of light backwards like this, which could also be similarly wonky and curved. This is very similar to the pancake case, but now we're in curved non-Euclidean geometry. But let's do a simpler example first. Here's a kind of silly situation where we've got this giant TV screen playing a video on loop that's whizzing past us at near light speed, which I've slowed down to just 1 unit per second. Here, I've assumed that the patch of spacetime we're looking at is isolated enough or small enough so that its curvature due to gravity is negligible. We can model this patch of spacetime as having Minkowski geometry everywhere, which, remember, is that pesky little geometry that spacetime locally has at any point when zoomed in, which is exactly what makes it different from any normal smooth surface we're used to that instead looks visibly flat and Euclidean when zoomed in. The 4D coordinate chart I'm using for the ray tracing here is represented by this little diagram called a Minkowski diagram, containing only the coordinate axes of the chart where interesting stuff is happening. Now, the nice thing about Minkowski geometry and the chart that I've chosen is that the axes here actually have the physical meanings of time and space, but only from the perspective of observers like us, at rest with respect to the floor. So our world line in green here is perfectly vertical, because we're only moving in time and not in space. And our moving space-like surface is always perfectly horizontal, and it always cuts through this pattern parallelogram here representing our TV screen in the same color everywhere along the cut. And what's cool here is that this space-like surface is literally the entire 3D view of the world being shown right now. And you can see how the place along the slice the parallelogram gets cut exactly lines up with where we see the television screen in the display, where the colors represent the time code of the looping video that each column of pixels is playing from left to right, with red at the beginning of the loop and blue at the end. Okay, and at the moment, let's just ignore the time delay problem of light and revisit it later. But now, watch what happens if we tilt the camera's trajectory just a little so that it moves at a speed of, say, 34% the speed of light in the direction of the TV. Not quite enough to keep up with it, but certainly enough to start seeing these strange effects. It stretches out and the video gets all jumbled up. And it's just really fun to play with this and see what it looks like at different tilts. But if we have a look at our chart here, we can see why this is happening. As we tilt our world line, our space-like surface also tilts inwards towards it like a pair of scissor blades, and it cuts through multiple colors at once. So we see different parts of the video playing simultaneously at different parts of the screen. And we can even do this for accelerating world lines, which gradually speeds us up from rest to match the TV speed. Alright, so if the space-like surface dictates exactly what we'll see inside this produced image, the question is, given some arbitrary world line like this, how can we compute the tilt of our space-like surface at every frame? This isn't so hard in a Minkowski diagram, where the rule is very simple. Just compute the tangent line to the curve and then reflect it across the diagonal. That's cool, but what about for other charts for general spacetime geometries, like inside this Schwarzschild chart? And in general, how in the world do we even calculate anything inside a coordinate chart if everything is so distorted and wacky? Well, the secret lies inside a special mathematical object in relativity that comes with each chart, which I've been kind of ignoring up till this point, called the metric tensor matrix. Here's what this magical matrix of numbers looks like for our Minkowski coordinate chart here. This kind of matrix comes packaged with every coordinate chart. Here's the one for our Schwarzschild one, and it's so powerful that it basically encodes everything there is to know about the geometry inside this coordinate chart. This is the tool that allows us to do things like measure angles or lengths, test which lines are actually straight versus curved, and perhaps most importantly for us, even how to draw a straight line given a starting position and direction, which is exactly what we'll need for the ray tracing here. In fact, some people even use the term metric interchangeably with spacetime or geometry because it completely defines everything about a patch of spacetime in terms of a coordinate chart. And it's actually one of the terms in the famous Einstein field equations that people solve for, which is where all these coordinate charts and matrices come from in the first place. Alright, let me stop hyping it up now and just tell you what it does. Now, get ready, because this is going to sound kind of dumb, especially for an object I'm claiming is this powerful. What this matrix does is very simple. Given two vectors stemming out from any point in our chart, it simply tells us how to compute the dot product between them. Trust me, it gets cool, okay? So let's go back to our Minkowski example, where the metric tensor matrix is just this constant diagonal matrix of plus and minus ones, which we can actually truncate down to this first 2x2 block since we're only working in 2 out of the full set of 4 chart coordinates. Okay, so let's consider this point along our observer world line and compute the dot product between the tangent vector, call it u time, and its reflected version along our instantaneous space-like surface, call it u space. To do this, we can express these vectors in terms of a basis aligned with the coordinate axes, given by, say, et hat pointing up and ex hat pointing to the right. So maybe u time equals some component a times et hat plus a second component b times ex hat. And because we've defined u space, this vector along our spatial slice, as a perfect reflection of u time across the diagonal, it's just given by b times et hat plus a times ex hat. Now if we dot these together as usual like this, we'll get a value that doesn't respect the geometry, because we've completely ignored what we know about charts and how they can arbitrarily distort things like vectors. So instead, let's use our metric tensor matrix as a tool to combat our chart-induced delusions here very simply as follows. Just insert this matrix in between the vectors, sandwich right in between, and matrix multiply away. And when the dust settles here, we're just left with 0. So our vectors were perpendicular all along, even though they don't appear that way in our chart. And in fact, we'll always get the same thing if we repeat this whole calculation on any such two pair of vectors, with one pointing along some observer world line and the other along the corresponding space-like surface. And so a really cool structure starts to emerge here. Let's do something a bit weird now. What if we take some arbitrary vector v, given by some linear combination a times et hat plus b times ex hat, and we dot it with itself using our little matrix. Quickly working it out, we get b squared minus a squared. So if v is wider than it's tall, such as any vector pointing along an observer's space-like surface, the self-dot product is positive, and we call this vector space-like. Meanwhile, if a is greater than b, such as for a vector pointing tangent to an observer world line, its self-dot product is negative, and we call this vector time-like. And finally, if v is perfectly diagonal, the terms cancel out to 0, and we call it light-like. Altogether, this is the light cone structure associated with this point in our chart. But because the metric tensor matrix here is constant everywhere in our chart of Minkowski geometry, every point has this same light cone structure. Meanwhile, for our Schwarzschild chart, where space-time is curved due to gravity, the metric tensor expression is dependent on where you are in the chart. But what's amazing is, if you compute these self-dot products using it at each point, you still get the same sort of light cone structure everywhere, only a bit more distorted in some places than others, like here, or maybe rotated elsewhere. And as it turns out, we actually get this light cone structure from Minkowski geometry popping out from every metric tensor matrix corresponding to any old chart of spacetime geometry. The reason? Because any old patch of spacetime, as we said before, when zoomed in, locally has Minkowski geometry, because it turns out that any old metric tensor matrix of some random chart of spacetime geometry can always be expressed as a sandwiched product involving the Minkowski metric tensor for some invertible matrix M, depending on the point at which we are evaluating this metric. And now watch what happens if we take the dot product between two vectors stemming from that point, where eta is just the Minkowski matrix above. we can regroup these terms like so, and we notice that this dot product is actually nothing more than the Minkowski dot product, except acting on linearly transformed versions of our two vectors, which is why no matter how distorted a spacetime chart, every point inside it will have some kind of such light cone structure. So what do these light cone structures sprinkled all over our chart actually tell us? Well, the cone itself at a point is the set of all directions with self dot product 0 under our metric. And so they're all the possible directions that a light ray passing through this point can enter and leave at. And so if we have a mystery curve inside our distorted chart like this, if it perfectly grazes all the light cones along its way, it's a ray of light. Meanwhile, if it's a curve that passes through this bottom quadrant of every light cone structure along its journey, called the past light cone region, and exits through these top future light cone regions, it's an observer world line. Or maybe it misses both these regions everywhere along its path, entering and leaving through only the space-like directions, in which case the curve is on a space-like surface. Isn't that neat? This is one of the many beauties of the metric tensor matrix. Even though the axes of a messy coordinate chart might not always represent space or time, we can tell a lot about the patch of space-time being represented, having drawn out this light cone structure everywhere. Alright, finally we can start describing our 4D ray tracing algorithm. This is also a ray trace demo of Minkowski spacetime, where we've got a scene full of objects and a bunch of spheres representing different observers whose world lines we can choose to follow if we play the currently paused animation. Because this is Minkowski spacetime, we can do all our ray tracing calculations inside a chart with a simple physical meaning. It's just a reference frame of the checkerboard floor again. The only difference now is we've chosen to represent this 4-dimensional coordinate chart using a picture with 3 axes instead of 2 to get a better understanding of the relevant motion here. Currently we're looking through the perspective of an observer that's at rest with respect to the floor, so our world line is perfectly vertical in the chart, and the associated space-like surface, which actually looks like a surface this time, is still perfectly horizontal. We can also imagine the light cone structure at each point in our picture here, where this time the cones actually look more like cones. But those same principles of how we can classify certain curves as before still apply. Alright, now watch what happens if we pick a different observer world line to follow. Again, the space-like surface starts tilting, and we start seeing these really cool length contractions again in the direction of our motion. If we also choose to model that time delay of light we talked about before, it looks even cooler, with all of this crazy field of view distortion. Okay, so what's going on here, and how do we take some point like this on our world line and trace rays from it in our coordinate chart to produce these images in real time, or these black hole images? The secret is really borrowing a standard trick from normal ray tracing, but adopting it to our setup. In a regular ray tracing implementation like in Blender, even though it's typically easier to trace the actual ray of light in the same set of coordinates that the rest of the objects in the scene are described in, centered at some world origin, it's often easier to initialize each ray's direction vector, the direction we want to shoot that ray out from, in terms of a basis aligned with our camera. And then we can transform that direction vector into world coordinates, which is where we do the actual tracing, to check which rays intersect any objects in the scene. We can use the exact same idea here, except instead of having our rays being traced inside a simple 3D environment, we trace them inside our wonky coordinate charts. But to initialize those ray directions, we compute and use a 4-dimensional camera basis at the instant we want to trace our rays. So remember, at any particular point along our camera's world line, the current space-like surface there represents what our observer currently perceives as space. And in this ray tracing setting here, without all that field of view distortion caused by the time delay of light, that space-like plane right there literally represents the slice of the world that we're seeing right now. And although it looks tilted in our chart representation here, we know that this is Minkowski geometry, so every space-like vector that it contains is actually perpendicular to the world line's tangent. And we can actually see this for vectors like these two right here if we rotate our view sufficiently and check whether the angles they make with the diagonal are congruent to the angle made by the tangent vector. Now here's the key. If we can find 3 such spatial vectors in our surface that, in addition to obviously being perpendicular to the world line's tangent, are also perpendicular to one another, then we've got ourselves a 4-dimensional camera basis. In the TV example, for instance, if we pause at some random point along this wacky world line, even though these two vectors from before, u time and u space, don't look perpendicular in our chart, they are as far as the observer is concerned. They form a basis, capturing how the observer instantaneously views spacetime at this point. And we can picture it like this to empathize with our observer. You can kind of think of this as another spacetime chart centered at where the observer is, but really it's just the observer's instantaneous viewpoint of spacetime under a linear transformation, which helps us better understand how the camera instantly perceives the world, with its space-like surface now coinciding with the horizontal axis, so that it actually appears perpendicular to the world line's tangent, which is now aligned with the vertical axis. And if we hit play, you can see that the parallelogram's colors cut by the space-like surface in both the diagrams always match. But in this bottom diagram from the observer's perspective, we can see that the changing length of the cross-section matches the length of the TV we see in the ray-traced image. But what's great about this linear map connecting these two views, given by this matrix whose columns are literally just the two basis vectors as seen in our chart, is that it comes in handy when converting vectors that are easier to describe from the observer's perspective into the chart's language. For instance, if we consider a vector along a light-like direction like v equals 1 minus 1, multiplying it by our matrix, we see that the two columns just get subtracted and the result points in the corresponding light-like direction in the chart. And if we choose to shoot a space-like ray, say literally along our space-like surface, say v equals 1, 0, multiplying it by our change of basis matrix maps it perfectly into the tilted surface in the chart, because it literally just selects the first matrix column, which is the first space-like basis vector. Back in our higher dimensional example again, the picture looks a bit different, but the main ideas remain the same. It's just that here, instead of needing two observer basis vectors to visualize the observer's frame of reference, we need three of them. The world line's current tangent vector, and two vectors on the tilted space-like surface, which are also perpendicular to one another so that we've got a valid basis. Now, our chart, being a chart, makes this basis look all scrunched up, but we can imagine a nicer picture like this one from the observer's perspective that you get under the proper change of basis map, which is now a 3x3 transformation matrix whose columns are the three basis vectors as they appear in the chart. And again, if we shoot space-like rays along the horizontal space-like directions inside this observer's instantaneous frame of reference, they all get mapped to the tilted surface sitting inside our main chart. There's one interesting difference in this higher dimensional picture though, which is something subtle that happens to light-like vectors under our now 3x3 transformation matrix. Turns out, light-like vectors still get mapped to light-like vectors in the chart, but they kind of swivel around the light cone like so, depending on how tilted the space-like surface is. And this is ultimately what leads to that crazy expansion of our field of view, when we enable our light-based ray tracing mode here. Isn't that cool? Alright, now to reach the final ray tracing setup, we have to remember that the full picture of our main coordinate chart is 4-dimensional, and that's what we actually need to trace our rays in to produce our images. But that's rather impossible to visualize. Up until this point, we've been visualizing our coordinate charts in lower dimensions, just to make them simpler to understand. But how do we make sense of their full 4-dimensional glory? The best we can do is kind of abstractly imagine our camera's true world line passing through this 4-dimensional coordinate chart, and a set of 4 orthogonal basis vectors centered at some point along this trajectory, with one time-like vector pointing along this world line and 3 space-like ones pointing along the now 3-dimensional space-like surface. But because it's a coordinate chart, these vectors when drawn in the chart would look all scrunched up. And even though we can't really visualize this, we can still build a 4x4 transformation matrix using these basis vectors as the columns in order to easily talk about ray directions in a cleaner, observer-centric reference frame. For now, let's ignore the time-like component and only focus on the space-like part. This is where we'll say our camera's sensor of pixels lives. In a lower dimensional representation where the space-like surface looks like a plane, it might look something like this, where instead of a grid, it kind of looks like a line of pixels instead. Anyway, the camera's eye will be located at the center point of these axes here, because that's where the observer currently is located along the world line. But what about our grid of pixels, the camera's sensor? That can be pointed in any which direction along the horizontal. And in my implementation, it changes all the time when I move around my mouse. And handling this requires an additional pesky little linear transformation, but let's just say for simplicity, it's pointed this way. Now, All we have to do is, for each pixel, say this one right here in the ith row and jth column, compute the vector from the eye towards that pixel in terms of our three spatial axes. Very simply, like this. For some constants c1 and c2 in terms of I and j, and where f is the focal length. And bam! We have ourselves a ray direction vector expressed inside the observer's reference frame, which we can now map back into our coordinate chart using our 4x4 transform. Oh, wait. We've only expressed this vector in terms of our three spatial basis vectors so far. What about the temporal component? Now, this is where we have some leeway. Remember that whole light time delay problem? We can either just ignore it and set the temporal component of our ray equal to 0, in which case the light ray just travels instantaneously through the space-like surface. But to properly handle it, we have to remember what ray tracing is doing. We're tracing the light rays in reverse out from our camera sensor in order to determine where they must have come from in the observer's past before they reached here. So in terms of the light cone structure inside our observer's reference frame here, what we'd really need for the ray to be is light-like and pointing along the past light cone's diagonal direction. So let's just normalize the whole 3D spatial component to be unit length in space and set the temporal component to -1. So it'll perfectly point diagonally downwards, inside 4 dimensions. And that's pretty much it. We can transform our space-like or light-like vector from our observer's frame of reference into our chart using our 4x4 transformation matrix. And just like that, we've got a ray position and a ray direction inside our coordinate chart, which we can use to trace our ray. Now thanks so much if you've made it this far, but at this point, you might have 2 major questions left unanswered. The first is, we kind of always assumed we readily had access to that transformation matrix, these set of 4 basis vectors describing our observer's frame of reference. In our charts of Minkowski spacetime, you might be able to think of some sort of ad hoc method to easily calculate these because of that simple reflection across the diagonal rule. But what about for general charted spacetimes, where the definition of what it means to be perpendicular at a given point in the chart might be based on some rather arbitrary value of the metric tensor matrix there? A common method I've seen in many black hole implementations is a well-oiled trick from linear algebra called the Gram-Schmidt process. I won't detail it here, but in a nutshell, you can start out with one vector in the basis we do know, like the time-like tangent vector to the observer world line, and then follow this neat process where we start with some arbitrary guess for the other 3 vectors, and slowly shave off the components of those vectors which are parallel to the others. In our case though, we'd have to replace the dot products used in this process with our metric tensor-induced dot product, so that the final basis vectors we're left with are actually perpendicular to one another in terms of the space-time's geometry at the observer's location. And the second most pressing question you might have now is, given this initial ray position and direction, how do we actually trace the dang ray inside our coordinate chart? And here, I'm going to refer you to some other excellent videos already on this topic. I know, a ray tracing video without describing how to trace the rays, but I honestly think the setup and intuitions covered in this video are the hardest part here if you want to implement this yourself. You pick some space-time geometry that you're interested in visualizing, choose a valid coordinate chart in which you want to trace your rays, initialize a time-like observer world line, and use the metric tensor dot product to build a linear transformation using Gram-Schmidt that lets you calculate the initial ray directions. Then what's typically done to trace the ray is use what's called the geodesic equation. But this requires computing the Christoffel symbols here by hand, which depend on the metric tensor matrix. But there's this really great alternative discussed in this wonderful blog post you can check out, which allows you to sidestep this whole process and have a general purpose implementation for any metric at the expense of some performance, using this quantity called the Hamiltonian. And I actually use this method in some cases to also trace out the observer world lines and space-like surfaces themselves too. There are lots of other delicious details to discuss here, but perhaps I'll save them for another Now Slice. And that's about it. See ya!